All right, guys, we are looking at the last chapter, chapter 5, your relationships in triangles. So we started off by looking at some of our special segments and some of the special properties that went along with those segments. So the first one we looked at was the perpendicular bisector. Now, its point of concurrency was the circumcenter. Oh, sorry, I cannot spell today. There we go, circumcenter. And it is equidistant, meaning equal in distance, to the vertices of the triangle. Okay, so let's take a look at a special picture that we have here. All right, so for our properties, again, in our triangle, oops, I'm gonna make that a little bit nicer. Oh, where is it? There it is. Oh, sorry, that's a teeny tiny little triangle. All right, let me zoom back in here. All right, there's our triangle. Turn that off. Okay, so for these to have perpendicular bisectors, all right, we have to start from the we don't have to start from the vertex here. Perpendicular bisectors cut each side in half. There we go. So we need to find the middle of all three sides of your triangle. Oh, can't really see the purple too much. Let's change that to yellow. Now, on each side of these dots are congruent pieces, because those dots, because of the bisector part of this, they are sitting at the midpoints of those sides. So on either side of that dot, we get congruent pieces. Now, if we draw the segment coming off of those dots, it might go through the vertex, but again, it doesn't have to. Perpendicular says that that segment should make a 90-degree angle with that side. So let me get my 90-degree boxes all the way around, and all three of these segments should cross at the same place. And so there's my 90 for the last one. So again, that dot, we don't actually need that extra. That dot where all three of them cross, that is the circumcenter point. And again, that dot to all three corners is congruent for all the way around. So if I erase just a piece of these segments, so I'm going to go back and redraw these segments, but just to their 90s. Okay, so I just erased the top part. That dot to all three corners of the triangle, all three vertices, is what is exactly the same. That's when it says equidistant. So that dot to all three vertices is exactly the same, and that's what that means. Oops, I apparently wrote that in the wrong box, so I'm just going to move it over. Okay. So again, we've got midpoints on the sides. So just some of the things that we want to remember. Midpoints on the sides. You've got right angles at the sides. Okay, and again, the circumcenter, like it says for the property, equidistant to vertices. That dot is equidistant to all of the corners. All right, let's look at our next one, angle bisector. An angle bisector's point of concurrency is the incenter. And an incenter is equidistant to the sides at a 90-degree angle. Okay, so when we're drawing the angle bisector, it's a little bit bigger. All right, angle bisector starts at a vertex, or more specifically, it cuts angles in half or into two equal parts. And we saw this at the beginning when we did chapter 1, when we talked about bisected angles. So again, we need to look for the congruent curves. All right, so let's make another triangle here. Okay, so there's our triangle. And again, at all three vertices, like the property says, we start at the vertex and we have to cut each of these angles in half. That is not in half. Let's try that again. That's better. All right, so there's one. I'm going to do the same thing to the one on the right. Okay, and then I'm going to do the same thing to the one at the top. Okay, and the dot where they cross, that is the incenter. Now, one thing I haven't drawn yet is because each of these lines are cutting those angles in the triangle in half, we should have the congruent curves. Oops, wrong color. We should have our congruent curves in each of those angles, because each of those lines is splitting that angle into two equal parts. So the angle at the top split in half, the angle in the bottom right split in half, and the angle on the bottom left split in half. So that's what it means by look for those congruent curves. Now, this one specifically says, again, based off the property. So I'm going to erase this, these points for these lines for a little bit. I'm going to redraw them, but only to the dot. Okay, so that incenter is equidistant to all three sides of this triangle at a right angle. Now, that doesn't mean this case that on either side of the 90 that is congruent. That's not what that means. But that means that dot to all three sides with that 90. Get the last one here. Those are all the same length. Okay, and again, those dots on the sides of the triangle are not midpoints. We don't have the congruent dashes there. And it's a lot easier to see with this piece. Those two lengths are not the same. The top piece is much shorter than the bottom piece. Okay, so just keep in mind, incenters do not connect midpoints. They don't go to midpoints. All right, let's do our next one, your median. The median point of concurrency is the centroid. A centroid has a couple of formulas with it, and we'll take a look at those formulas in just a second. One of them was that, remember, the centroid cuts the segment, the median, into a shorter part and a longer part. So we have the short piece was 1/2 of the long piece. We had the short was 1/3 of the whole way across. And then we had two formulas for the long. The longer part of the median was 2 times the short, or the longer part of the median was 2/3 of the whole entire way across that segment. Okay, so let's take a look and see how we used these formulas. So I'm going to get the properties up here. All right, So again, medians connect vertices. So we go from vertex to a midpoint. Okay, so I'm just going to draw a real quick one. Again, if this is the median, vertex to midpoint. So on either side of that dot, I need the dashes. Okay, so look for those dashes. All right, so let's get that picture up here. And again, it doesn't have to be the same kind of triangle over and over and over again. Notice this one is a little different. All right, so let's get all of our vertices up here. And again, I need the middle of each side. So it's actually better if I get the midpoints first. All right, so all three of those dots on the edges of the triangle, those are my midpoints. And when I connect the midpoint to the vertex, that's when I make a median. Again, there's 3 of them in every triangle. And there is my centroid dot in the middle. And again, for this one, that one centroid dot cuts each median into a shorter part and a longer part. So I'm actually going to leave those lines there and write those labels in. I'm going to make that a little bit smaller. So we have a short part on the blue one, on that first median. There's my short part for the other one, and then my third one, my shorter piece here, and that means the other side has to be the longer piece. And again, it is visually longer. And then my last one. All right, so there's all of my pieces. So again, each of those short pieces are half the length of their longer part, or it takes 2 of the shorts to make one whole long, and it takes 3 of the shorts to go all the way across. All right, so I'm going to leave that triangle there for you guys. So there's our labeled picture. Now, the last one we looked at was the altitude. Its point of concurrency was the orthocenter. Okay, and remember, this one could be inside the triangle. So let's get a little more specific here. The orthocenter will be inside for acute triangles. It will be on the side for a right triangle. Oops, nope, sorry. If it is a right triangle, it will be on the right angle. So let me fix that. There we go. So on the right angle, for a right triangle. And then our last one, outside for obtuse triangles. And again, that's just for the orthocenter. Now, specifically when we draw altitudes, altitudes connect, oops, gonna make that a little bit bigger now. A vertex to 90 degrees. All right, now altitudes can be in one of three places. This is where we said they could be one on inside, on a side, or outside the triangle. So let's take a look at what that might look like for our different kinds of triangles here. Okay, so we have an acute triangle here. Once it adjusts, there it is. Turn that off. Okay, so again, your in-center, I'm sorry, not your in-center, your orthocenter from each vertex, oops, make that a little bit bigger. We make a 90-degree angle with the side. And let's get our last one. Oops, I'm gonna make that one a little bit bigger. Okay, and there's our orthocenter inside. And all the altitudes are inside when the triangle is acute. The second one is when we have a right triangle. Okay, so there is my 90-degree angle. So from each vertice to that 90 degrees is where we get our altitude. And same thing when the angle is right there, there's our last side. And notice all three of these converge at the 90 degrees, and that's where we get on the side. All right, now the last one is when we had the obtuse triangle. And I'll move that just a little bit. Okay, so we have an obtuse triangle here. And again, if I start from each vertice and draw that 90 degrees to each side, this is where we had to draw the sides outside of the triangle. So I'm going to need a little more space here for this one. Now, all three of these lines, even though it's kind of hard to see right now, if I keep going with all three of these, that's when they will eventually cross, but they cross outside of the triangle. And that's where we say they can cross outside, or your altitudes could be outside of the triangle. Okay. All right. Now, once we looked at your special segments and triangles, we talked about what are the requirements to make a triangle altogether. And one of those things we had were the triangle inequality. Some of those facts we said that the largest angle in a triangle is opposite the largest side. Okay, and the smallest angle The smallest angle is across from the smallest side. And then we talked about, again, the requirement to make a triangle. The sum of the lengths of the two shorter sides. So remember, this needs to be the shorter two sides of a triangle must be greater than the third side. So let's try some of those properties and see what we get. All right, example 1, which segment is the longest? So we need to find the largest angle in these triangles. Even if there's 2 of them, find the biggest angle. So we've got the 2 obtuse triangles here. So the obtuse ones are my bigger angles. But which one is the largest? 123 or 120? 123 is my biggest. It is across from side PS. Which means segment PS is my biggest side. Now, same picture, which line segment is the shortest? So that means I need to find the smallest angle out of all of these. So I actually need to find those missing angles, those acute angles that are in there to figure out which one is my biggest. I'm sorry, which one is my smallest. So let's get those other angles. All right, so for the triangle on the left, every triangle makes 180. So we've got 123 plus 28 is 151. Take that out of 180, and I get 29. Okay, so right now 28 is the smallest. So let's get the missing angle in the right triangle, or the triangle on the right here. So 120 plus 30 gives me 150. Take that out of 180. And my leftover angle there is 30. All right, so out of all of my numbers, which one is the smallest? That would be 28. It is across from the shortest side, which would be P to Q. So PQ is the shortest side. All right, now let's test out what makes a triangle or not. And again, we need to add up the smaller 2 numbers. They have to be bigger than the third number, the leftover, in order to make a triangle. All right, so I have 14, 9, and 2. 9 and 2 are my bigger numbers. They are 11. Add them together. If I compare 11 to 14, 11 is smaller, no triangle. Let's try the second one. 11, 12, and 23. 11 and 12 are my smaller. Add them together. 23. If I compare that to the leftover 23, they are equal, no triangle. Letter C. Again, find the 2 smaller. They don't always come in the first 2. 5 and 3 are my smaller. That makes 8. 8 is less than 9. No triangle. And then the last one, 5, 8, 12. 5 and 8 are my smaller. They make 13. 13 is bigger than 12. There is my triangle. All right. Now, one extra thing I did give you when you're dealing with do you have a triangle or not is the equation to find the range for third side. So I'm going to write it down over here on the side. Okay, and this was a formula that we covered. We had to find the difference of the 2 numbers. it has to be bigger than the difference, but less than the sum. And so that's again, when they just give you two numbers, you need to minus the two numbers and then add the two numbers. And then your missing side has to be between them, but not equal. Because remember, equal does not make a triangle. So let's do our last part here. Point P is a circumcenter. So again, circumcenter, equidistant to the vertices, and it's creating midpoints. List any segments congruent to each one given. So let's find all our equal pieces first. All right, so if P is my circumcenter, first off, point P, the circumcenter to all three corners, is exactly the same. So P to B is the same as P to A and the same as P to C. And that answers one of my questions right there. AP is congruent to segment BP. And it's got an extra one, segment CP. All three of those are congruent because again, circumcenter to corner, all the same. Now let's find the rest of the information. We talked about how those dots where all of the 90s are midpoints of the sides. So on either side of T, it is congruent. Either side of S is congruent, and either side of R is congruent. So R to B is the same as R to A. S to A is the same as S to C. And T to C is the same as T to B. So let's see if we can answer any more questions now. All right, B to T is the 3 dashes, so it has to match with C to T. So segment CT. AS is the segment with 2 dashes, so it has to match with CS. Segment CS. So there are lots of other congruent pairs, but again, it's just making sure we know which piece we're looking for. All right, our last one deals with the centroid. So these are the short and long formulas. So let's put all of our information into the picture. So it says UC. So U to C is 12. And again, that is a longer part of UK. So there's my short. So before I do anything else, the shorter piece, short is 1/2 of the long. So cut 12 in half, 12 divide by 2, or 12 times 1/2, and I get 6 for the other side. Let's keep going. E to M. That is the whole entire way across. We said that the short is 1/3 of the whole entire thing. So guys, if my whole entire thing is 36, I need 1/3 of 36, which is 12. And again, just a reminder, 1/2 of 12 is where we got the 6. So right now, there's my short, there is my long. I have 12 for UM. And now the longer piece, that's one of our other formulas, is 2 times the short, or in this case, 2 times 12. So 24 on the other side. Now let's do our last one. U to J is 5, which is my short. UD is the long. So like the one we just did, 2 times the short, that gives me a length of 10. So now that we've got all our numbers, let's answer our question. So K to U has a 6. C to K is all the way across, 6 plus 12, so 18. E to U is 24. All right, M to U has the 12. Okay, our last piece, J to D is the entire way across, so 15. U to D is 10. Okay, guys, so I hope you enjoyed reviewing a little bit about our special segments and special relationships and triangles. Again, this was our most recent bit of information, so hopefully this even helped you finish up some of those missing assignments we may still have for this unit. So please don't hesitate to reach out to me if you have any questions at all. Bye, guys.